Hello, everyone. Good morning and good afternoon, depending where you are. I'm Dr. Sophia Su. I'll be the new webinar chair for 2022. So if you have any suggestions and comments or complaints, feel free to let me know, okay? And if you have any suggestions for a particular speaker or a topic that you would like to hear, let me know. Okay, so our first webinar of this year is from Dr. Xuan Bi from University of Minnesota. Xuan's research mainly focuses on the statistical learning and information system, and he has PhD from University of Illinois at Urbana-Champaign. Then he has a postdoc at Yale University before he joins the University of Minnesota. Xuan is an expert in recommender system and data privacy, and today he'll tell us something recent developments on data privacy. So welcome, Xuan.
Thank you very much, Zhihua, for your invitation and the great introduction. It's actually my great honor to present my work actually here at the SLDS webinar. Yeah, but I suddenly become very nervous because you said I'm the first speaker. I didn't aware of that when you invite me, but thanks again for the invitation. So today, as you said, that I'm going to talk about data privacy. So to better utilize everybody's time, I think I will start from the motivation and the necessity of doing data privacy protection research, and then followed by some recent development and some nascent studies of data privacy protection mechanisms, and then use the rest of the time, I will develop one of our recent work with Professor Xiaotong about a distribution invariant privatization. So hope that works for everyone. So first is motivation. Why do people care about differential privacy? Why do we need to do research in differential privacy? Sorry, data privacy, not differential privacy yet. So data privacy as a very broad field actually has been increasingly important in the big data era. I believe most of you have heard about it, about knowing that population-wise, people are getting gradually getting awareness of the importance of privacy protection. As an online user, people care about whether their clicking history, purchase history, demographic information has been voluntarily shared by other parties. So this is population-wise awareness driven, driving people to care about privacy protection. Also because the fast development of AI, people have to judge whether AI in the future can be trustworthy, either that can be reliable, robustness, and privacy is also one of the very important issue or open question that has to be addressed. And also from the government side, there's a regularization, there are regulations, and there are data-related policies enforce individuals and companies to be obliged to a data privacy type of rules. And also there's, from other side, there's increasing demand of data sharing. So let's introduce the motivation and the necessity of doing data privacy from each stakeholder's perspective. First, from the end user's perspective, don't look at the joke at this moment. First, let's concentrate on the text on the left-hand side of my slide. From an end user's perspective, anonymization is not enough. I guess many people know it. So even though my data say is de-identified, there's still ways to identify that I am the person who clicked something, who purchased something, who viewed something. For example, if I say, hey, the tallest person in this room is very clever, even though I don't point to who he or she is, people in the same classroom know immediately who I'm talking about. So that means anonymization is not enough. The second awareness that I want to create is that sometimes data that are seemingly or ostensibly non-confidential may still contain or reveal very sensitive information. In this work, people say that, okay, even movie ratings, which seems very innocent, that can infer sensitive information such as political preference, because you can use that information to link to people's public reviewed information such that it can reveal sensitive information. And also some browsers claim that there are 57 ways to identify anonymous user. Even you go on a browser and go with the anonymous mode, don't try to do that. It's, to some extent, is not so effective, as people are still ways to identify who you are based on ways such as like IP address, clicking behaviors, or website that you frequently visit. And also there's some misuse of privacy protection techniques. Now you can look at the joke on the right-hand side. So there's a student say, hey, I don't want to go back to school, and reporter ask him why. The student say, hey, can you pixelate my face? Reporter say, sure. And then only in the last picture, you can see that student's face is pixelated perfectly. Let's say that's privacy protection. It's very effective in this figure, but not in the first photo. Because my roommate has body odor. So is the privacy perfectly protected? Obviously, everyone can see it's not. But to some extent, I won't say fully, but to some extent, this is a status quo of privacy protection in the real world. That from a whole procedure as a whole protocol, let's say, maybe at some phase, some steps, the privacy is perfectly protected, but at the upper stream of the procedure, maybe data are not so perfectly protected. So this is just the kind of the motivation from end user's perspective. Why do we need to care about privacy protection? And also from a managerial perspective, maybe a little bit controversial, a little bit counterintuitive. As before I dive into privacy research, I do not see this side of motivation. So actually, it's almost like an oxymoron that the protection of privacy is actually for the promoting of data sharing. So you may ask me, hey, why do I want to share my data? So this is on a condition that when data is perfectly privatized, when this very perfectly privatized is safe to use, then people or companies may stand to start to think about how do we share the data to merge data together, privatize the data, or sometimes even intermediate statistics rather than raw data together to create better data usefulness, to create a higher social welfare. And this actually promote cross-platform cooperation, and it's actually a underexplored field with great potential. People say it's a gigantic industry in the next 5 to 10 years. And if you search online, there's a lot of startup companies in Europe, in China, and in the United States, where there are third parties that kind of organize, orchestrate institutes or organizations such that they can share not data, but intermediate statistics privately, such that they can cooperate. So this is start to become one norm that in the future that data can be used in this way. And who are actually those major parties that are interested in developing or promoting data privacy protection mechanisms? Here are at least some that I'm aware of. And of course, feel free to chime in if you know more parties that are interested in this industrial area. First, of course, large IT companies are very interested in data privacy protection. They have visible platforms and apps that can be freely or not freely used by users, and they collect rich data from the users. And they, of course, care about the privacy of their customers because, you know, if data are breached to some extent, customers are not satisfied. This can be the ramifications of this is actually very, very bad. So large IT companies are actually care about the data privacy, and their advantages is just like I said, they have visible platforms and app which can collect rich data for usage for social welfare. And also there's another party that also care about data privacy is firms actually in those domains. For example, financial companies, medical research companies, and now more recently, smart manufacturing companies are also start to care about data privacy. If you know more industry that care about privacy, feel free to let me know. And their advantage is that they have domain specific knowledge. They can contribute from their side. For example, on medical research, there's a very nascent Nature Medicine paper published just this year, if not last year, that talk about the prediction of respirators needed for COVID-19 patients. That is a study that is orchestrated across about 20, if not 30, I don't remember the clear number, across the globe, instituted across the globe, who privately contributed data that can jointly predict what's the accurate number of respirators needed by each hospital, needed by each patient based on their current condition. So this is actually a very effective or very impactful study because of the jointly use of data across the globe, which are not necessarily, to be reviewed to some extent, but through using the privacy techniques, patients' data are perfectly privatized and protected, but their utilities can be used through sharing intermediate statistics and or perturbed values of those intermediate statistics. So these are actually those domains who really care about data privacy. And also, more recently, startup companies are also chipping in this area through contributing in privacy protection mechanisms per se. and also through building AI systems, etc., that are actually very helpful in this whole game. So these are the major parties that I'm aware of, which are actually very interested and have high motivations of doing privacy research. And of course, as a machine learning researcher and as a data scientist, from research perspective, why data privacy are important, why people really care about it. First, I want to clarify that research in data privacy, unlike research in some other data science or statistics fields, is actually highly interdisciplinary, if not transdisciplinary. Because as you can see, hey, machine learning is also interdisciplinary. The statisticians and computer scientists are doing machine learning from their own perspective. Why do you say that data privacy is particularly highly interdisciplinary, if not transdisciplinary? Because not only because there are many technical fields of people from those fields that do research in data privacy, which contains statisticians, computer scientists, electrical engineers, but also mathematicians and people who do cryptographies. But also because it's not only related to data, but also may related to hardware development and also related to, say, legal, ethical, and other areas of research. For example, we may have blockchain, which from a hardware level that can protect data, but we may also have a homomorphic encryption that mathematically transform the data into a form that cannot be decoded as a cryptography method, but also from statistical point of view, we can perturb the data or resample the data to protect the data at a different level. So as you can see, as in regular machine learning research, people are having a common goal, say given X predict Y, but in data privacy, the protection is actually multiple layers, have a lot of hierarchies. So the protections are very different. Personally, I encounter some papers that in other fields of data privacy, you can see that the angle that they look at it is very different. And not to mention that recently there's also other fields that are gradually catching more intentions about data privacy. As I'm in business school, and I know that a lot of my colleagues are actually also doing works in data privacy, but from a different angle. For example, people care about the economic value of data privacy protection. Say, if I'm a company that I have data privacy protection, well, another company does not have such technique. What's the actual value of having it? And if I'm a company who does not have data privacy protection techniques, how much should I pay to get these whole systems equipped or installed? And also there's incentives of privacy protection, say as stakeholders. Is there any strategic behaviors that stakeholders may play? For example, if some of you may know the federated learning system, say if I'm a server, how should I perform to actually optimize my utility? And if I'm just a regular client, regular player, regular participant, how should I play? So the strategic behavior of stakeholders are also things that people are start to think about, and also how do we incentivize them such that they can fairly contribute to the system, share their privatized data without compromising the whole system. This is another field. Also, we talk about like other aspect of data privacy from the legal, ethical, behavioral, societal, or even psychological aspects of data privacy. Say, I encounter some scholars who do these aspects. Say, if I'm a privacy protection company, what design of the web should I use such that the customers can more believe that this website is trustworthy in terms of a privacy protection? Given that all the privacy protection technique is exactly identical, how can we make customers trust me that their data's privacy are perfectly protected? It's from a psychological aspect. And also we also encounter some scholars in the legal aspect that say, hey, how do we actually make new laws actually that can accommodate new regulations that can accommodate the recent development, the nascent trend of data privacy protection? So these are some motivations from different stakeholders. And also I just want to provide one use case that can let you see why this is important and why we can do data privacy and why it can be beneficial. Suppose there's a manufacturing company A that has very rich product data, specifications, production volume, etc., all about their own production and their own product. But they are interested in predicting a new product sales in the future. Say I'm a flash sale company, I do a lot of fancy fashion stuff, but this year we developed and design, developed, and intend to release something really new, really different from the other products, what's the product's sales in the future. So obviously, this manufacturing company doesn't necessarily have consumer and distributors data because they are like in the regression setting, they can be used as independent variables, such as demographic information, sales amount at each outlet and each grocery store, but stores. And hence the prediction result can be rough because you only have your products information. But suppose now there's an online marketing firm B, which has consumer demographics, and the data solution company, which has distributors data. Each of them has some features that the manufacturer A wants. And privacy protection techniques actually allow the company A to purchase those features. So if you only have Y and some X, now you can purchase more X, more independent variables without getting access to their raw data. This is very important. You do not sell raw data to your partners. You sell data that are perfectly privatized, such that the regression result, as you can see, can become much better. The prediction of the future outcomes can be more accurate. And at the same time, B and C get paid either through a lump sum as a one-time transaction or through some subscription fees as a long-term partnership. Well, A gains revenue through having a more accurate model. So this is in reality, this is a business model, how things can get done. And also like this is vertical integration in a sense that the multiple variables are merged, and also you can merge horizontally. Say I have 1,000 users information, you have 1,000 users information. After data privatization, only after data privatization, can I purchase 1,000 users information from you such that I can have 2,000 users information and make a better model. These are all things that people are currently considering. You can check the online literature, the tons of literature talking about how this can be done in an elegant way without sacrificing or compromising users' privacy. And there are tons of methods, like I mentioned, that from different levels, statistical level, from machine learning level, mathematical level, from cryptographical level, that do data privacy protection. That the first two, differential privacy and federal learning, are more related to statistical data science and also fields that I personally have research on. So if you are also interested in these fields, feel free to reach out to me. I believe we definitely have a lot to talk about. And the security multi-party computation and homomorphic encryption are also important fields of doing data privacy. I know little or basic concept of them, but not very deeply. And lastly, there's a trusted execution environments and zero knowledge proof that I know very little about. So in this talk, I will mainly introduce differential privacy. Several reasons that I listed here. First is because it's so relatable to statistics and data science. As sometimes a data perturbation or resampling methods, they can be very relatable, and they are also executable without involvement of other parties. Unlike federal learning, if some of you know a little about it, it actually involves multiple parties to share data privately. For example, you need to have a server as an orchestrator, and you need to have independent clients who actually are contributors. But as differential privacy, if you are just individual researchers or a lab of teams, then basically you can do it just by yourself without the participation of other sites. And also they have very effective and broad applications in many domain areas. And as you can check the literature, and I will show you some. So that's one of the reasons that I will focus on differential privacy. But if you're interested in the rest of them, especially in federal learning, we also do have some researchers in that areas as well. All right, so what is differential privacy? So actually it's proposed by Professor Dwork in 2006, which basically quantifies the notion of privacy for downstream data analysis. They quantify, which is very important. Say, we can talk casually, chit chat about what is privacy, say, hey, my data are breached and your data are perfectly protected. So what does it mean? So here, differential privacy gives you a mathematical definition that says, hey, data are quantified, they are privatized, to what degree? So it is actually a very strict definition, recognizing that privacy can still be undermined even after data de-identification. For example, the tallest person in the room example that I mentioned earlier. So a strict definition in a sense that if you satisfy differential privacy, actually a lot of existing privacy definitions are also satisfied and enjoyed. For example, it is not enough to satisfy differential privacy if the traditional cryptographical definition, such as distributional distance is sacrificed. If two data sets or a data set after privatization or perturbation only has a small distributional distance with the original data, it's not enough. For differential privacy, we require more to actually satisfy this definition. So that's why we see it's strict, very strict. And there's commonly, to the best of my knowledge, correct me if I'm wrong, there's actually two ways that people use to achieve differential privacy. One is through noise injection, or statisticians always call it data perturbation. And also we have resampling, and sometimes through a synthetic data generation. So these are ways that are commonly used, and I'm not saying that there are no other ways. There are definitely other ways, but these are commonly used. And before I introduce the mathematical definition here, I give you the high-level broad introduction of what is actually defined in differential privacy. Basically, it says it ensures that the substitution of any single observations, even the most extreme one, for example, the tallest person in the room that I mentioned earlier, in a data set would have a small impact on the publicly shared information. For example, suppose you are interested in sharing the average height of people in the classroom, and that's the true knowledge, true information. You do not want to share that. And then you say, hey, if I switch or substitute the highest person with the average height person, and then I calculate another average, will that be very different? Then differential privacy says that if your data set is differentially private, is protected by differential privacy, then regardless of whose data being substituted, the result won't change that much. So that's very powerful. So mathematically, this says that if Z is actually, is small z is the original data set, Z prime is the data set, the original data set, but with one observation being substituted by another observation randomly. It's not necessarily random, but arbitrary. You can switch the tallest person's height into an average height, or even into the shortest person's height. And then they say after the privatization, those two data sets or the summary statistics of the two data sets, either way, won't be distinguishable. So the probability ratio will be bounded by e to the epsilon, where epsilon we call it a budget of privacy protection. You can imagine that the larger epsilon guarantees that the range for the ratio to be larger, such that the privacy protection is actually weaker. And the small epsilon actually enforces strict privacy protection. As you can see, if you set epsilon exactly to be 0, then they say the data privacy, the probability of these two observations by shifting another observation has to be exactly identical. This is very strict. So you can, to some extent, you can imagine there's a trade-off there. It's like a bar tuning from a spectrum. Do you want a higher privacy, or do you want the privacy to be low, but on the other hand, you want a higher data usefulness and accuracy? We'll get to that later. So far, this is the definition for differential privacy. And there's a broadly used in many areas. So in research areas, of course, machine learning and artificial intelligence, I suggest you to look at Professor Jordan's paper. And also there's use in biomedicine, in epidemiology, and sociology, if not other areas. I do see a lot of areas, but slides has to be limited for space. So I just listed a few here. And they are used by many IT companies: Google, Apple, Microsoft, LinkedIn, Amazon, and Facebook, and you can name it. They all use differential privacy to some extent. And you can see all the reference, you can check the year. Most of them are very recent. So that's why I say this is a very nascent field where new things are coming up every day. And in 2020, this is more convincing. For the first time, differential privacy is used in the decennial census. So this is another way to demonstrate the usefulness of differential privacy. And this is the application side, how it is used in practice. And the next slide is about how to achieve differential privacy from not necessarily a statistical point of view, but statistical, machine learning, data science, computer science point of view. They include literature, but not limited to, for example, the most iconic differential privacy algorithm is called Laplace mechanism, proposed just by Dr. Dworkin herself in 2006. And also exponential mechanism, also an iconic method that is done by resampling, which is proposed in 2007. And also Dr. Ducci also proposed some method for doing differential privacy. And also there's other methods that are widely used. Professor Wasserman, Joe, and Professor Slavkovic and Professor Meng, they all have some contributions in these areas, as you can see. This is not a complete literature. This is just some include but not limited to this literature. There is a rich literature that you can search online that are doing very excellent works in differential privacy. So I will start from a Laplace mechanism, as this is one of the most iconic and basic differential privacy method. And also another important reason is that it provides the framework for the derivation or the proposal of the proposed method, our method. So that's why we introduce it here. It's not saying that other methods are not important; they are all equally important, but just for the derivation of the slides of the subsequent slides. So to achieve differential privacy through the use of Laplace mechanism is actually not hard. Suppose X is the original data that you collect, whatever data you have. And the way to achieve differential privacy is simply to perturb it or add a noise to it. But the noise here has to be carefully chosen. It has to be a Laplacian noise such that it can guarantee heavy tails. So compare with Gaussian or normal distribution, Laplacian distribution actually have a heavy tail because the exponential term is actually exponential just to the x, not to the x squared. So the tail is actually heavier. And it's very simple, just by adding a Laplacian noise to the original data, and now you can claim your data is differentially private. But just the degree of privacy protection is still open to discussion. But at least doing such a simple procedure, we can protect the data from regular use. And you can see that large value of this is a slightly abuse of the notation. It's not large E, but large variance of E guarantees a high privacy. Because the noise is large, the noise signal to noise ratio becomes lower. But as you can see, a large noise actually guarantees a low accuracy or low data usefulness of the data because the original information in the data has been obfuscated. An advantage of doing this Laplace mechanism is that it's very easy to implement. Everyone can do it at home. Just open R and generate some Laplacian noise, add to your original data, regardless of the size of the data, whatever. Easy to guarantee the privacy of the data. And also have low computational costs. Just one addition here, very easy. And also, just because of all these advantages, they do have some downsides. So first, as you can see, it altered the original data distribution. So suppose we're talking about age or we're talking about gender, then just simply adding a Laplacian noise to dummy variables or to some ordinal or categorical variables obviously change the distribution. Not to mention the continuous distribution. If your original data is Gaussian distributed, then adding a Laplacian noise also changes the distribution. Some weird thing may happen. For example, you may see negative age. You may see 0.7 as your, say, marital status or some binary variables. And of course, there's additional efforts you need to pay to post-process the data such that you can still follow the original data support. But even though you truncate all those negative age and change them into 0, you can imagine that the original data's distribution has been drastically changed. Because to satisfy rigorous rigorous differential privacy, usually the noise that has to be added to the original data is very high, such that you may encounter a lot of negative age, which means after truncation becomes 0. You figure out that the released data contains a lot of people whose age is 0, exactly newborn baby. And another theoretical restriction is that Laplacian mechanism actually require boundedness to guarantee differential privacy. What does it mean? Boundedness means it has to have a bounded support. Data cannot range freely. For example, Gaussian distribution is not bounded. It ranges from negative infinity to positive infinity, although you can truncate it, but it's still essentially unbounded. So this is actually frequently violated. People have to assume that the observed observation is from a truncated normal or something else. That without boundedness, that Laplacian mechanism do not guarantee differential privacy. In our paper, actually, we prove that as long as a linear perturbation method, regardless of whether you use Laplacian noise or other noise, differential privacy can never be guaranteed because of this requirement. And third is that if you do this for each of your variables independently, then obviously the dependency structure has been changed. Of course, you can use copular, you can use correlated Laplacian noise to tweak this a little bit, but still, when the true data has no true distribution, when the real data has no true distribution available, then how do we add a correlated noise such that the perturbed data still follow the same dependency structure as the original data? Becomes extremely noisy and challenging. So because of all these three disadvantages, some existing literature or some practitioners that in industry I talk with, that they prefer, to use differential privacy to some extent, but not to all the as pervasive as for federated learning. I'll not talk about that for this moment. But at least a bottom line or a consensus view is that there's always a trade-off between data privacy and accuracy, as I mentioned in the early slide. If you impose a very large noise, basically it's called a small privacy budget epsilon. It basically means better privacy protection for sure, but less accuracy for data sharing. The data usefulness is actually more also important. If we want a perfect data privacy, we can encode all data as 0 or as an NA not available, or we can wipe out all the data and obliterate our hard drive, and through the obliterated hard drive in the depth of the Pacific Ocean, that's perfectly private, but that does not guarantee any data usefulness. So that's why I say it's almost like oxymoron that privacy is actually for better data useness. And here is the trade-off, and this is a consensus view is what I mean. Okay, that's the status quo and some existing, introduction of existing and recent development in differential privacy. If there's any questions or quick questions, feel free to chime in. Otherwise, I can leave questions to the end. And then I can start to introduce our contributions based on the status quo, based on the development of the Laplacian mechanism. So first, me and Professor Xuan in 2021, we developed a distribution invariant privatization mechanism. Literally, you can see what we mean. So we intend to do all the three things all together. So first, we intend to asymptotically preserve the original distribution. We are aware that if distribution is changed, is altered, then basically no downstream statistical analysis can be done as if the original data were used. So we try to preserve the original distribution not only for a single univariate distribution, but also for multivariate distribution such that it can include all inherent structure. And also a very good relaxation is that it does not require boundedness. And I'm aware that recent work started to be aware of this condition, and there's also some relaxations. And eventually, because of all these good properties, it reconciles both high statistical accuracy and strict differential privacy. So let's introduce it one by one. It looks very, exaggerating, but after I introduce the method, you will see, hey, this is exactly true. And the method actually is very simple. This is actually one of the, if I want to say, one of the most informative slide in my whole deck. So if you understand this slide fully, then you see, hey, the method is nothing magical, but it indeed follows all those previous mentioned properties. So suppose Z here, let's do it from the archetype. Let's do it from the simplest case. It's a univariate continuous variable that follows the cumulative distribution function F. Very simple, univariate, very simple, continuous. And let E follow the previous notation, be a Laplacian noise. Then we have the following. First, we already say that Z follows the CDF F. And based on the probability integral transformation, because Z is a continuous distribution, then IFZ as another variable follows a uniform distribution, right? And then by adding the Laplacian noise, a uniform distribution plus a Laplace distribution, we just use the probability integral, the convolution of the probability density. We're aware that it follows a distribution called G. I do not provide the explicit form of G here, but the explicit form of G is available because this is the convolution of two non-distributions. And this is a convoluted CDF of the uniform 0, 1 plus a Laplacian 0 with some variance B. And it follows G such that if we apply G here again, this follows a uniform distribution. And finally, because this is uniform distribution, if we apply F inverse again, you can see that Z tilde, which is a privatized Z, back again follows F. So this is the key of the proposed method. And there are two things that it's important to note. First, by using this nonlinear transformation, we eventually end up with the tilde that still follow F, which is the original distribution. Of course, this is all in the hypothetically, because we assume that true distribution is none. We assume that there's a continuous variable, but just given all these are true, the perturbed values still follow the same distribution, regardless of whether it's normal, it's uniform, it's exponential, whatever. And second, it guarantees differential privacy because it is the differential privacy, the noise, is being injected or imposed on Fz, which is the bounded value between 0 and 1. So Laplacian noise is added to a bounded value. So at this step, it guarantees differential privacy. And based on Professor Wasserman and Zhou paper in 2010, once this step is differentially private, as long as all the subsequent transformations are not data dependent, they are all differentially private. So I basically verbally or orally proved one of the theorems in our paper. So it is differentially private, and after some non-transformations, it is still differentially private. But this transformation guarantees that the perturbed value, the differentially private value, also follows the original distribution, which is the key. So I'm going to stop here for 1 second in case you want to digest a little bit more. But hopefully the two messages here are super clear to everyone. First is that after this transformation, it guarantees that follows the original distribution. And second is that because the Laplacian noise has been added to the bounded value, it guarantees differential privacy perfectly. All right, so I assume that this is clearly conveyed. So the next step is, as you can imagine, what we're gonna do. Here's a brief flow chart to visualize what we do here. So suppose you have arbitrary distribution, not necessarily normal. If, for example, you have a mixture distribution, that as long as you know the distribution, after the transformation, it becomes a uniform distribution. After you add up Laplace noise, it becomes convoluted value, which is similar to normal, but is slightly heavy denser than normal. And we use the green color here because it's now already differentially private. And now we use the transformation here back again, is back to the original distribution, but it's now differentially private. So this is basically a summary of what we have done in the paper. And this is the archetype. And from here, we're going to generalize this archetype to discrete distributions, multivariate distributions, unknown distributions, and etc., empirical distributions, whatever you name it. And yeah, so the first step we're going to do is now we still suppose that F is none, but don't worry, later on we're going to generalize this to unknown distributions. But suppose it is none, suppose now it follows univariate discrete variable. And what we're going to do, we are kind of a lazy person. We do not want to propose a new set of mechanisms to protect the privacy, but we are thinking, can we put this data set into the continuous framework such that the original one in the previous slide can still work? So naturally, what we are thinking is about how to continualize this discrete variable z such that we can still use the previous archetype that we just mentioned in the previous slide. So the way to do it is very simple. If you look at the CDF, suppose this is a very vanilla type of a discrete CDF. This is just a binary data. And it has a probability of P1 to observe 1 and a probability of 1 minus P1 to observe 0. So the original discrete data CDF is ladder shaped. And continualization is never hard because you can simply connect data by connect all those probability mass. And the way to connect the first one is you arbitrarily create another point. We say just if this is 0, then 0 minus 1, and it becomes -1. Connect this point to the previous one such that although this is not smooth, this is not differentiable, but this is continuous. And how do we create a variable to meet this distribution? It's also easy. We just define a uniformly distributed variable u, which is independent of z. Then we define a new variable called z minus u, and obviously this variable follows this continualized distribution. And how do we convert it back to the original distribution? We just take the shading function. If this value is from -1 to 0, after the shading function becomes 0. And if it's become 0 to 1, then after the shading function, it becomes 1. And they're not supposed to have any other values. So the probability densities are only non-zero in this region. So in this way, we create or alternatively, we continualize the originally discrete variable into a continual variable such that we can apply the mechanism that we mentioned in the previous slide. And this is how we achieve that. Suppose we still have Z follow F, where F here is a discrete CDF. Now, after the definition of this V here, it follows a continualized CDF, which is the one that on the the bottom right corner of the previous slide. This is a continualized. And then we use a previously mentioned differentially private mechanism. After this whole nonlinear transformation, we get a V2 that which, because of the injected Laplacian noise, it follows the original, it follows the differential privacy, but also because nonlinear transformation, it follows the original FV, the continualized distribution. And then we use a regular shading function that can map the continualized distribution into the original distribution. So the whole procedure can be done for discrete variable. You may have questions, hey, if the discrete variables are not evenly spaced, how do you do that? Then the trick thing is that as long as you create this VU dependent on the original value of Z, such that it is continuous within the two support point of the discrete variable, then you are still good. In the paper, we have a theorem to demonstrate that, but here just verbally, I will show you that this is still doable. And then the corresponding shading function is not just a regular shading, but maps the perturbed value to the nearest probability mass above its own value. Is fine. And here, the two things are still satisfied. First, because of the injected Laplacian noise, again, it follows differential privacy. And second, because of the use of the previous nonlinear transformation, it follows exactly the original CDF. And this can also be done for mixed distribution. If you have both a continuous part and a probability mass, this can still be done. I do have slides in the appendix if you're interested, or you can read our papers. They have a very clear derivations or explications of how this can be done. And how do we do this for multivariate variables? So once you know how to do it for a univariate variable, then for multivariate, it's not hard. So we can just do it sequentially via the probability chain rule. Again, let's suppose that the multivariate distribution is none, such that all the conditional distributions are none. And then what you can do is privatize the first variable and then privatize the second variable given the perturbed value of the first one. And then you do the P's variable conditional on the perturbed value of the first one until the P minus 1. For each of them, the mechanism is different because they use the corresponding functions that we introduced in the previous two slides. If it's discrete, use the discrete privatization function. If it's continuous, use the continuous one, such that based on a sequence of those univariate, we call DIP, distribution invariant privatization. You use a sequence of those DIPs, you can privatize this multivariate distribution. And later on, I will show you some simulation result that the relationship between all those variables after privatization are still held the same. For example, if you do a logistic regression before and after privatization, the result won't change much. If you do a prediction, we tried a supervised and unsupervised learning, result doesn't change that much. And these are, of course, these are very utopian. This is utopia, and these are a case when true distribution is given. So what we're gonna show is next. Suppose a true distribution is not known. So how can we do it? So one of the referees gave us a very good suggestion that you can claim that there is a public data set of the same distribution. Suppose the referee is here, thank you very much. This is something that we haven't think about. So one example is that you may argue that how do you find a data set that has perfectly same distribution online? Where there's some examples, not always, but they do have some example. For example, American community survey data, which is public, and the census data, which is private, are from the same distribution. They are all surveyed from the American people, just one being 1% each time, the other being 100%, almost 100% each time. They're from the same distribution. So if you do have ASCS data available, you can use that as the public data set to privatize census data. If you don't have public data set available, another way to do it is to just like training and testing set that you have for machine learning task. For privacy, you can also split your original sample into two subsamples. One being we call the holdout sample. We use the holdout sample to train the empirical CDF of the distribution. And then we privatize and release the other subsample based on the distribution trained by the holdout sample. And you may ask, hey, how do you guarantee the privacy of the holdout sample? First, let me get this very clarified. Holdout sample is fixed it's never been altered. As you remember, differential privacy is defined on altered data set. If you alter one observation, how the probability ratio changed. Here, holdout sample has always been fixed when selected. You randomly select it for sure, but when selected, it's fixed. And then it's never allowed to be altered, to be queried, or to be released. So it's perfectly safe. It's secured in a let's say a disconnected hard drive to build the empirical CDF. And once the empirical CDF is built, once the release sample is privatized and released, the holdout sample, you can just simply remove it. Let's just say wipe it out or obliterate the hard drive, throw it into the depths of the Pacific Ocean, whatever you want to do. So holdout sample is never released. So it's not actually subject to the judgment of a differential privacy, which is not applicable because of there's no data point has to be altered. And using this way, the trade-off is that, well, so let me first say the good thing. The advantage is that it asymptotically guarantees the distribution. So you can use the privatized data just as if the original data were used, because it asymptotically follows the same distribution as if the raw data are used. The downside is that there's no trade-off. Basically, in terms of privacy and accuracy, the trade-off very thin. You can see in the simulation result later. Regardless of how large the Laplacian noise you want to impose to it, or even a larger noise imposed to it, heavier tail than Laplacian noise, the distribution are still preserved because of the nonlinear transformation we imposed. So in that sense, the trade-off is completely bricked, is reconciled, because regardless how you change it, the distribution is followed. But where's the new, say, there's no free lunch for sure. So where's the sacrifice? The sacrifice is to release the data now is not as large as the original data set. That's downside. So you say use 25% of data for a holdout, then you only have 75% of data to be released. And we show a machine learning task, a movie recommendation task, where you have to use a large percent of the data for training, but because 25% data loss, now you have a small training set. And we also have a network reconstruction task where a number of sample size is smaller than number of parameters. Then a small sample size means that the training size is even smaller given the large parameter size. So these are the downsides, which basically transfer the trade-off between privacy and accuracy into a trade-off between the good estimation of the CDF I've had and the availability of the released sample. So hopefully this is get clarified at this moment. So we quickly have some theoretical result. I know this is not the most interesting part people read, so I simplified all those languages so people can understand that clearly. Basically everything has been covered verbally based on what I said. Differential DIP, the proposed method is differentially private. And the privatized sample follows the original distribution if the distribution is none, or asymptotically so if the distribution is unknown, but if the public or the holdout sample goes to infinity. So basically, if you have enough sample to estimate the true distribution, then basically the released sample follows the true distribution. But if you don't have enough sample to estimate the true distribution, at least the released sample follows the empirical distribution of the holdout set. And the computational complexity is basically P is number of parameters in the sequential probability chain rule. N is the sample size, and there's an additional log n term because you have to sort the distribution to estimate it. And guarantees differential privacy, preserve distribution, and computationally efficient. And the rest of slides won't take very long because they are all numerical demonstrations of the effectiveness of the performance. And there do have some very strong competitors. We compare here is Laplacian mechanism that is a benchmark for the proposed method. We really appreciate that without it, there's no proposed method. And we do have exponential method, which is very good, which can accommodate high sensitivities that works well for discrete data, but is computationally very, very challenging for continuous data. So for continuous data privatization, we do not compare with that. And also we have Professor Ducci's method. We also compare with it. It is very flexible and actually is a solution to many canonical families of problems. And we also have the non-private result as an oracle because non-private theoretically provide the most accurate result. And all those privatization methods basically to some extent sacrifice some accuracy. So we compare who is actually the closest to the non-private version is actually the best. The first one we do is we generate data from a true distribution where the distribution ranges from Bernoulli, binomial, Poisson, geometric, uniform, beta, normal, and exponential. You can see they are both either bounded or unbounded, discrete or continuous. Not too many studies in the existing literature that do distributions like this because they are unbounded, very hard to handle. But in our study, we try all those, and we will show you result momentarily. We set a privacy factor, which is called budget, to be absolutely equal to 1. You can check, you can check existing literature that this is actually very tight, very strict privacy protection. And here's the result, maybe too small for you to look here. The blue line here, down here, the blue line, this is a non-private version. So we do the parameter estimation. For example, normal distribution, we estimate the mean. Poisson distribution, we estimate lambda, etc. And it's the estimation with respect to sample size. And the blue line is actually the true estimation, not the true, the non-private estimation. And you can see this red curve is actually the proposed method. In all of the 4 situations, it's basically nearly perfectly aligned with the non-private version, saying that distribution-wise, there's no information loss. Well, these are the proposed method. You can see the error compared with the proposed method is still large. And exponential mechanism is actually a powerful mechanism in the sense that these are all discrete distributions, but exponential mechanism has result the closest to the proposed one. In the next slide, we compare still the same thing, but these are all just changed into continuous distributions, uniform, beta, normal, and exponential. You can see the proposed method still aligns with the non-private version nearly perfectly. And they also all enjoy the same rate of asymptotic convergence. With the sample size increase, the estimation of the unknown parameters is getting much better in square root n rate. While the existing methods do not necessarily enjoy the large sample property, and they are very distant from the proposed method. And look at here, this is a log scale. Okay, these are the studies where the true distribution is given. Now let's look at studies where the true distribution is unknown. So here we use 3 real-world data sets. We do have some simulations that are assuming the true distributions are unknown, but due to the time limitation, I put them in the appendix slides and also they're in the paper. If you're interested to see how our method performs when the true distribution unknown in a simulated setting, can refer you to there. But here I demonstrate you the real world data set. First data set is University of California system salary data, which is also a data set that I got from Professor Ducci's paper, also public available, collected in 2010. There are 252,000 employees whose salaries were available in the setting. And the average salary here show you this is non-private value is 39,000. And the standard deviation is about 53,000. The goal of our comparison is to just simply to estimate the mean. But every method privatize the whole sample individually. Do your own stuff. And then after privatization, we compare the estimated differentially private mean and see which one is actually the closest to the original one. Is actually the best performance. So that's the thing we do. Every method do exactly the same and compare the mean difference. And here is the relative mean difference is actually reported. So just show you how the histogram looks like. This is the original UC salary after the log transformation. This is how it looks like. And this is the proposed method after privatization. After privatization, how the histogram looks like. You do not see nearly no difference. Just by eyeballing it, there's some unique difference here. This one is slightly higher than this, but other than that, I do not see much difference. And but individual-wise, every unique individual's data point is privatized. For example, originally the value is 6,000. After privatization becomes 90,000. That's possible. So the values are changed. Individuals' value are changed, although still correlated, but the distribution does not change. If you're interested in a distributional population result, it does not change. And the second data set we compare is Prodigy's bank marketing campaign data, which is available in the UCM machine learning repository if you're interested in data set. About 30,000 respondents are available, and the response variable they are interested in is a binary one. Is whether the respondents are interested in a term deposit. So it's basically a logistic regression task. We do have some covariates, but here, look at that. We have continuous variable, we have binary variable, categorical variable, corresponding to age, employment status, marital status, education, lung status, etc. Tons of variables of different types. Some have multiple categories, for example, marital status. And we are interested to see before and after data privatization, multivariate data privatization, can each method still have the logistic regression, estimated regression coefficient, that is very close to non-private version before data are privatized. The evaluation metric is callback labor divergence. And before I introduce the result, I have a third data set to show you. Is maybe some of you are familiar with it. I do recommender system research in the past few years, so this data set is very familiar to me personally. Movie Lens data set collected 25 million movie ratings from 162,000 users over 59,000 movies. Movie ratings are simply just ordinal, from 0.5, 1, 1.5, all the way to 5. No cover is available. So the goal is not just to privatize to calculate the mean, but to calculate the movie recommendation. We randomly split the data by training and testing, and the training data is privatized, the testing data is non-privatized. We want to see how the collaborative filtering recommender system, basically is the matrix factorization method, can train the movie recommendation system while still privately, but also accurately predict the user's preference. Evaluation metrics is root mean square error. There's only 2 slides here, so don't worry, I'm going to finish it very soon. So here's the result summarizing all the 3 data sets comparison. Here's a summary of the features, characteristics of those data sets. So here's the size, the sample size, and this is the type of the data, continuous, multivariate, and discrete. Dimension of the data are also here. They're not super large tests. As personally, my Mac is not super powerful to handle 10 million, but hypothetically, they should be similar. Tasks, mean estimation, logistic regression, collaborative filtering. And here's the result. Let's look at them vertically. For using salary estimation, DIP actually provide a mean estimation, relatively mean estimation has about 0.4 difference compared with the existing method. You can see the large difference, at least 10 times, if not 100 times better. And exponential mechanism, like I said, is only for discrete variables, so it's not available here. For bank marketing data, it's logistic regression. We have to privatize each variable individually, and the proposed method, because of its ability to take care of the dependency structure across multiple variables, you can see the logistic regression, the callback labeler distance is also very small. And this one actually is infinity because a lot of predicted probability becomes 0 or 1, dichotomized or polarized. So the callback labeler divergence is infinity. Again, exponential mechanism not available because of the contains continuous variable. The last one is actually the most comprehensive one. Exponential variable becomes available because these are all discrete variables. It's the closest to the proposed method, while the other 2 are a little bit large. And in all those settings, privacy factor is said to be 1, which is very strict. That's why some of the existing methods explode. If the privacy is to be relaxed, some method performs actually better. DIP holds 25% of the data, and you can see across all different measures and across all different tasks, DIP is the best performance. We do have many different simulation studies, for example, linear regression, network reconstruction, parameter estimation, and all those type of, we done a lot of numerical study, trust me, a lot of studies. If you check our archive paper online, you can see that. And hopefully that can demonstrate the proposed method's effectiveness. And this is only a quick summary. Data privacy is becoming critical in the big data era. We discuss the status quo of data privacy and the importance of differential privacy in particular. We introduced a proposed method called distribution invariant privatization, guarantee 2 things at the same time. First, strict differential privacy for sure, without requiring data boundedness. Second, preserves the original distribution asymptotically if the original distribution is unknown, which allows and ensures data usefulness and accuracy for any downstream statistical and machine learning tasks. And we do extensive theoretical and numerical performance examines. So hopefully that's enough. So here are all the references that I mentioned in my talk. And well, thank you very much. Here's my email. If you're interested in data privacy or differential privacy or work, feel free to reach out to me. Very happy to discuss with you. Thank you.